The HR diagram. What is it? Well, that's what we're going to be talking about. The HR diagram is what, in astronomical parlance, is called a big deal. I joke, but yeah. The HR diagram is a big deal. It's a kind of graph. I can draw right here. Graph that you sort stars on. And you can understand a lot about a star from its position on the HR diagram. What does this mean? Well, it stands for Hertzsprung-Russell, which are the two guys who came up with it. We shorten it to HR because it's used so often. So, let's start. This is a graph, so let's start with the axes. The x-axis in the HR diagram is temperature. But it's graphed a little bit strangely, in which high temperature is over on the left side and low temperature is on the right side. Non-standard, but it is how it is, sort of. Now the y-axis is luminosity, the amount of light the star gives off. However, the HR diagram is kind of funny. It sort of has not just one x-axis, but two x-axes and two y-axes. In the context of stars, we can not only talk about temperature, we can also talk about the spectral type. As you may recall from last week's lecture, the spectral type that we currently used, as developed by Andy Jump Cannon, sorts stars primarily based on temperature. It's arranged on temperature. So, we can also put the spectral type as being like sort of a... Well, I've spread these out too closely, but yeah, let's get something like... something like this, right? And of course, this also can be thought of as color. And these are like the same axis. These values, spectral type, color, temperature, they're equivalent to each other for these stars. So, they're basically interchangeable. You can make a Hertzsprung-Russell diagram that has any of them as the x-axis. You can do a similar thing with the y-axis. One way to do it is luminosity, a description of the amount of light that the star gives off. But you can also use the equivalent measurement of absolute magnitude. Now, magnitude is kind of a strange unit of measurement in astronomy. It's a measurement of how bright something appears. And it's defined in a way that smaller magnitudes mean it's brighter. So something with magnitude 1 is brighter than magnitude 2. Magnitudes can also be negative, right? I think the moon is something like magnitude -4 for us, something like that, I don't know. So you can have negative magnitudes, you can have magnitude 0. It's kind of a weird system, a little confusing. Apparent magnitude is the magnitude that an object, the brightness, measures the brightness that an object appears to have to us sitting here on Earth. But absolute magnitude is the magnitude we would expect an object to have if we were looking at it from a set distance away. Maybe, I think it's like 10 light years, if I recall correctly. So, sorry. So, absolute magnitude is nice because it allows us to compare the brightnesses of different like stars and stuff on even terms, to where the distance that the star happens to be away from us isn't a factor, by bringing it to like this standardized length. Standardized distance that we're looking at it from. So, again, luminosity and absolute magnitude, they're different units, but fundamentally they mean the same thing. So you can have the HR diagram have a y-axis of either luminosity or absolute magnitude. So what does the HR diagram look like? And by that I mean, if you were to put a bunch of stars and arrange them on the HR diagram, each point is like one star. You take its temperature, you take its luminosity, you put it there, right? So what would it look like? Well, it would look like this. And this is kind of some of the key insights from the HR diagram. I'm going to adjust this a little bit. Okay, sorry, it was a little bit tough, but I'm gonna get it. This maybe. And then like, okay, that's better. Yeah, now we're cooking. And then, basically, by what I drew here, you'd have a bunch of stars in here, right? There are stars all over in here, but they're all in this general little band that's kind of shaped like this. This is, I'm going to actually write this underneath. This is the main sequence. Main sequence stars lie somewhere along here, based on how massive they are. High spectral type stars like O, B, A, etc., they're high mass. Lower mass stars are down here. And their temperature, their luminosity, it's pretty well, it matches up with this trend very nicely. So main sequence stars are somewhere in here, depending on how massive they are. Another quality of main sequence stars is that their lifetimes, the amount of time the star is going to exist before it somehow dies, is related to their mass and like their luminosity and temperature. High mass stars have short lifespans. They burn through their fuel quicker. High mass stars may only live for, a few tens of millions of years. Very short in cosmic timescales. Something like this might live for like a few 100 million years, You get the idea, right? It's like, the more mass you have, the brighter you burn, the quicker you go through all your fuel, and you run out and you die. So high mass stars have a short lifespan. Low mass stars have a much longer lifespan. Really low mass stars like M's can have lifespans that are like 40 billion years, even 100 billion years, I think. G-type stars like our sun, I think the sun is going to have a total lifespan of maybe something like 10, 15 billion years, pretty long. When you're smaller, you burn through your fuel less quickly. So, smaller, cooler, less bright, you burn through your mass less quickly, you have a much longer lifespan. That's a kind of important concept about stars. But I digress a little bit. So here's the main sequence. Here's where they fit. Then we have the giants. The giants sort of look like this. They're a little more spread out than the main sequence. But they tend to be in this area. They're brighter than the main sequence stars of similar spectral types like Ks and Ms. But they have about the same temperature, which that's kind of a different thing, but basically they're brighter because they have the same temperature but a bigger area to radiate that energy off of. So they end up being brighter as a result. So those are like the giants, like your red giants, some yellow giants, kind of normal giants. And then supergiants. Aren't a lot of them, but they're over here. I think there are also some like red supergiants. I'm actually not 100% sure about this. I'm going to go and check real quick. I'll be right back. Okay, so I just made sure that I wasn't misleading you. So basically, these are both supergiants, but there's not like this big kind of gap between them. There are supergiants kind of all in this area. Oftentimes they're drawn as being a little bit closer over here, not quite so many over here, because ones that are over here are quite rare. So you may see some diagrams that have supergiants just taking up sort of about that much space. But yeah, okay. So there you go, there's the supergiants. They're kind of up in this area. And then down here, you have the white dwarfs. White dwarfs are a particular kind of star remnant. They're stars that have already died, and due to the mass that they were at, they became very compact objects called white dwarfs. Our own sun is going to become a white dwarf when it dies, and they sit down here. As you can see, they are very hot, have a very high surface temperature, comparable to some of these like O and B type stars, but they're also much smaller, and so they give off way less light. So that's kind of the deal there. So, I think that about covers the HR diagram. I've got an assignment for y'all, just a variety of kind of relaxed multiple choice questions about the HR diagram. So I think y'all can do that now. I'm gonna In the next video, I'll be talking about the cosmic distance ladder.